much further ado, I'm happy to have Charles give us that.
All right. So let's see. So I know everybody was here at the last lecture, right? Yeah, all right. So last time I talked about some specific thing, which was power operations for Morava E theory. And I described a picture that involved something called descent for isogenies. And I want to talk about that some more, but I'm going to put it in a more general context. And then I'll come back to some things that I want to explain about that. So let me just set this up here. So if you remember from the first lecture, there was this gadget called the moduli stack of elliptic curves, smooth elliptic curves. So for our purposes, all you really need to know is that if you have a scheme S and you look at the collection of all maps into M, this is supposed to correspond to all elliptic curves C over the base scheme S. And of course, you have to interpret this in the right way. These are actually groupoids. So this is the groupoid of elliptic curves and isomorphisms over the fixed base. And of course, a stack, in some sense, represents a functor to groupoids. So this is sort of the only thing I need to know about a stack for most of what I'm going to talk about today. Now, it turns out that for any n, there's another object, which I'm going to call M isog n. And this is the stack that represents isogenies of elliptic curves of degree n. So let's just set this up. So here I'll have M isog n. That's a groupoid. What is it? Well, it's a collection of all F that are isogenies of degree n. So don't know if I've defined this. Well, it's a map between elliptic curves, so it's a map of curves that preserves the base point, and that's automatically a homomorphism. The isogeny condition means that it's actually, well, it's non-trivial. It's not the zero homomorphism. Or more precisely, since I have a family, it's defines a map that's flat and finite. And the n corresponds to the rank, which is the degree of this finite flat morphism, or if you like, it's the rank of the kernel of this thing. The kernel of an isogeny is a finite subgroup scheme of the curve C. But this also forms a groupoid. If you like, these are the objects of my groupoid. And the morphisms of my groupoid are squares consisting of an isogeny, another isogeny, and isomorphisms between the curves, making the diagram commute. So morphisms are diagrams. That's an isomorphism. That's an isogeny going across. Then parentheses. Okay. So this is also a representable object. There are maps that encode various obvious bits of structure. For instance, I have source and target maps that do the obvious things. Given isogeny, they classify the source or the target. It's useful to keep in mind a different description of this, which I've already kind of implicitly alluded to in the previous talk, which is if I think about, let's say, the source map, let's call it a little s, and suppose I have a map from a scheme S that classifies an actual elliptic curve, I can think about the collection of all lifts. So that, in some sense, corresponds to isogenies with a fixed source in degree n. Really, it corresponds to a certain collection of isomorphism classes of such. These lifts are actually in one-to-one correspondence with finite subgroup schemes, G over S of rank n. And the correspondence is, well, if I have an isogeny of rank n, it has a kernel, which is a finite subgroup scheme. Conversely, if I have a finite subgroup scheme, I can form the quotient. And that the projection map, the quotient map to the quotient is an isogeny. And So by what was called in the recitation last week the first isomorphism theorem, is that right? By the first isomorphism theorem, those coincide. All right. Very good. This map is actually a particular kind of map. It's representable. S, and for that matter, T, this is representable. This means the following. So let's take little s. Let's take a map from an affine scheme, spec A, which represents some curve over A. In stacks, we can form a pullback. And this morphism has the property that the pullback is always also an affine scheme when we pull back along a map from an affine scheme. I'm going to call this A sub isog n. So this pullback is always affine. From an affine over an affine is affine. In fact, more is true. In fact, the induced map of rings A to A isog n, I'll call it S because it's the pullback of S, is itself finite and flat of rank. So it's locally free, and the rank is equal to the number of subgroups of R mod z squared of order n. In other words, the rank of this map of rings, it's A sub isog n is a free module over A, is the same as sort of the number you would expect to get if you just counted the number of subgroups of order n in a classical elliptic curve. Yep. This ring depends on C. It depends on the map. So I did not include that in the notation. Typically, I'll have a fixed A, and then I'll pull back along it. Right. So you can form the following. So I'm going to write M isog without an N. It's the union of all these. And then out of this, I'll form a simplicial object called M dot. So M dot has M, and then M isog, and then I'll have the fiber product. And then we'll decorate these T and S and so forth. So the idea is that these are elliptic curves, isogenies of elliptic curves, composable sequences of 2 isogenies, and composable sequences of 3 isogenies, and so forth. The structure maps are encoded by the fact that you can compose isogenies. They form a category. So this is some sort of category object in stacks. So Mn S to Mn corresponds to sequences of isogenies defined over S. Right. Or equivalently, by this correspondence with subgroups, I'll just keep this in mind in case I need it, I can think of replace every isogeny in this list. Actually, what I'll do is I'll replace every isogeny from C0 to some CK with its kernel. Each of those gives me a kernel, which is some subgroup GK, and I get an ascending sequence of finite subgroup schemes. G1 up to Gn. This is G2. These are finite subgroup schemes. Or S. Right.
Charles, there's a category whose objects are elliptic curves and whose morphisms are isogenies.
Yes, over say a fixed base. Yes. For each S. If I look at its approximately, except that instead of being, if you look at maps of S into this, instead of getting a simplicial object in sets, you get a simplicial object in groupoids, because the value at each S, maps of S into M or whatever, is always a groupoid. So it's a simplicial object in groupoids. another way to say what this is, it's a complete Siegel object in stacks. That's all this is. All right. So having set this up, I can now talk about descent for isogenies. So let's fix a map of stacks. So I'll have some other stack y going to m. So I can think of this as classifying an elliptic curve or describing an elliptic curve over y. One way I can think about this that's a little bit different, though, is I can think of y as classifying some kind of structure. I want to have this picture in mind when I talk about this on an elliptic curve. So here's the picture. I fix my map, y over m, and now let's consider an arbitrary elliptic curve over some base s. I call that curve C. It's classified by a map to m, and I can consider the collection of all lifts. That's actually a groupoid, and let's just call that capital Y C mod s. So an element in this thing, I'm going to sort of pretend that this groupoid is actually a set, because in sort of the easiest examples to think about, it really is just a set. I'll go some examples in a minute. So I'll think of this alpha as some piece of structure that I've added to the elliptic curve C mod s. And then y classifies the curve together with whatever some extra structure, which in this abstract formulation is kind of hard to think about. But I'll call this a y structure. Let me do examples, because that makes it very clear. I just want to have the language to say things this way. Oh dear, I have to erase things. Where do we go? Here we go. So where's the spongy thing? This thing is slightly damp, luckily. So for instance, one example is the universal curve. So, let's call this y again. It's the universal curve. So if I take the corresponding construction y of some fixed curve, which is classified by a map from S. What is this? Well, this is actually a set. It's actually the set of sections of the elliptic curve. It's the S points of the curve C. That's all this is. So if I use the universal curve as my object over M, this is just the set of points. Actually, there's another implicit example on the board. I forgot I already did it. Actually, it was already here. M isog n over M. I actually already said that. The corresponding functor is the set of, if you like, subgroups of particular order. Here's one more example I want to refer to later. This is, uses the notion of a level n structure, little n. So a level n structure on a curve is a choice of isomorphism of groups from the discrete group z mod n squared to the n torsion of C. That's a subgroup scheme. And this is meant to be an isomorphism of group schemes over S. This is an isomorphism. And there's an associated stack of such things, which is called Mn. This is the stack of elliptic curves with a full level n structure. Okay. And then in this formulation, y, if this is y of a curve is just the set of level n structures on that curve. So these are the kinds of examples I might want to think about. This is a particularly nice example in that if n is big enough, I think if it's 4 or bigger, it's this object over this stack of smooth elliptic curves, Mn is actually affine. So if n is, I think, if it's large enough. Huh? Sorry? Is 3 good enough? All right. Let's just say if it's large enough, this is affine. And then, is it? I thought 3 doesn't quite work, but maybe I'm wrong. Maybe you're right. No, it's full level structure. 3 is good. So this condition here, that this is an isomorphism, actually forces n to be invertible. So one feature of this is that in this ring that defines this, n will be invertible. The other observation here is that this map is atal. So in the language of the first talk, this means that there's a commutative S algebra corresponding to this map, and that's TMF with a level structure. All right. Okay, now I can say what descent for isogenies. So we'll say y over m has descent for isogenies if there exists a map of simplicial stacks y dot to m dot such that, so first, y0 to m0 is the same as the given map y to m. So it extends the given map y to m. And 2, for all k, we have a square. Yk goes to mk. That's this map. And I also have y0 goes to m0. And these vertical maps I'm going to call S. But let me say what this is. I have a map of simplicial objects. And so I have lots of ways of building maps from the kth level to the 0th level. I mean the one that's associated to a particular map of simplicial indexing categories. This is the one that sends 0 to 0. If you think of this as representing a sequence of maps, then I'm just including into the first object. And the condition is this should be a pullback, or actually a weak pullback. And so it's the appropriate pullback for the notion of it for stacks. This is a pullback. So what this means is whatever the value of yk is, it's determined by knowing, or let's actually say it like this. To give a map into yk is to give a map into mk, that is a sequence of isogenies, together with data about the very first map in that sequence, namely a y structure. So they're both, I just want to identify those two things. So I'm going to say that that is the original map. Or if I want to be a little bit more flexible, I'll say it has a specified equivalence to the given map y to m. Okay? No, I'm saying it's extra structure I'm giving myself. Yk is implicitly defined, is implicitly determined up to equivalence because I've specified that pullback. And that tells you what the object yk has to be. However, there's additional data in the specification. It tells you what yk is up to equivalence. But there's additional data, which is the structure maps in the simplicial object. And that's really the new information. So the idea is that yk by axiom 2, yk, or actually axiom 1 and axiom 2 together, tell you that a map into yk picks out the following kind of data. It picks out a sequence, composable sequence of isogenies over S and a y structure on the first thing. Okay. The simplicial structure gives me some operations that I can do to these things. So for instance, let's think about y1. So y1 comes with two different maps to y0, which is really just y. Suppose I have a map S into y1 that classifies the data of an isogeny from C0 to C1 and a y structure on C0. That's called a source and target. This thing forgets about the isogeny. This just gives me C0 and alpha. That's because I have that pullback square that allows me to identify y1. The other simplicial map, T, does something different, and that's the new information. It gives me some way of taking the y structure in C0 and the isogeny and produces a map which classifies, well, a y structure, let's call it alpha prime, on C1. I'll think of alpha prime as somehow being alpha pushed forward along F. And this is the new information. So this operation, F lower shriek, which goes from y over Cs to y C prime over S, or I guess C0 and C1, the way I set it up, is produced by the first new simplicial structure map you have when you write down what y dot is. The first simplicial structure map that's not implied implicitly by the axioms 1 or 2. So that would be this one. And then the higher simplicial structure is saying that not only do you have these push forwards, but they're functorial. In other words, this is basically a really fancy way to talk about having some kind of functor from the category of elliptic curves and isogenies to something else, like sets or groupoids. In fact, if you're familiar with sort of infinite-categorical notions like, I guess, right vibration or something, I never know what the right terminology is. This is sort of just a version of that. It's just a way of talking about a functor. Okay. So this is just a lot of formalism to talk about a functor. So let's make an observation, which is what I really want to fix on. Let's suppose y is actually spec of a ring. Let's call this A0. And suppose this map is equipped with descent for isogenies. So I think on an earlier board, I observed that I could produce from this ring A associated rings A sub isogen by pullback, right? Let me write that out. Spec A0 goes to M, which is M0. Then I have M isog N, which is a part of M1. And then I can pull back, and that's what I called spec isog N. So we had these pullbacks. The new structure, the descent structure, when I think about what it means in the language of rings, says that the maps, for instance, the maps S and T, they're represented by maps of rings, which I'll call S and T, and they go the other way. And furthermore, I have other simplicial structure. For instance, I have, my simplicial object is gone. I have the middle simplicial map from M2 to M1. That encodes composition. So M2 to M1, which is the middle simplicial map, I think this is called D1. This is encoded by a collection of maps. A isog n n prime goes to A isog n tensor A isog n prime. And this is over A0, and I use the two different ring structures, module structures. So that's a map of rings. And then there are further consistencies. So in the last lecture, I talked about power operations from Robert E theory, and effectively I wrote down exactly this. The only restriction was in that case, I didn't have general n's. N was always p to the r, the power of p. That's the only difference in this formulation. Okay. Associated to this structure, and I'll just state this for this example where y is affine, is we get a category that I'll call mod y. It's maybe not a good category. Maybe it's descent. I'll decorate it with the word descent. So this is a category of A modules, A0 modules. So the objects are A0 modules equipped with structure maps psi isog which go from M to M tensor over A0 with A isog n by S. And these maps have to satisfy certain identities, which are like the identities for a comodule. That's exactly what I wrote for the power operations last time. Let me actually write down the square, which I'll have to do on a different board. But it's more or less the obvious thing. You have to write down something that says that composition sort of does the thing you want it to do.
Y still the spec of A naught?
Yeah, in this case, y is spec of A naught. I could make a definition for a general y over m that's representable. I guess by talking about quasi-coherent sheaves, but well, I could if I knew what that meant. My algebraic geometry is a little weak, I have to say. But certainly in the case where that's a ring, it's sort of such that. So I have to figure out how to write n1, n2, n3. You know how this is going to go. I'm not sure why I'm bothering to write this out. So I'm not even going to label them as this commutes. All these tensor products are over A with appropriately decorated with source and target, which probably goes like that. Right. So we get a category. Okay, so this was just a long discussion so we can figure out how to produce this category. That's why I introduced it. Let me give some examples. So let me first give examples of things with descent for isogenies. The universal curve, E over M. This has descent for isogenies. Tautologically, I have to tell you how, given a point in an elliptic curve, C, let's call it P, it's a section, in an isogeny, F, I have to tell you how to produce a section of C prime over S. How do I do that? It's F of P, right? Here's another example, which is not quite an example. A modified example. Let's take the stack of full level n structures. I want to push forward a full level n structure along an isogeny. I actually discovered that there's a little problem. Let's take an isogeny. Now, I'm assuming here that I have these subgroup schemes, C parentheses brackets n. These are the subgroups of the n torsion, the kernel of multiplication by n. F induces a map on the n torsion subgroups by easily, but it may not be an isomorphism. If isogeny, the isogeny F is of degree prime to n, then this is an isomorphism. Now, if I could attach level n structures to these things, let's say I have a level n structure on C, now, as long as I have an isogeny of degree prime to n, there's an obvious way to push it forward. Let's actually just call it F opposed alpha. If I have an isogeny which is not of degree prime to n, there's no obvious way to push forward the level structure. As far as I know, there is no such globally defined structure of pushing forward level structures for isogenies of degree that are not prime to n. So what we learn is that Mn over M has descent, not for all isogenies, degree prime to p, degree prime to n. This is kind of a more typical situation. You have some nice thing living over the elliptic moduli stack. You expect it to have descent for isogenies, but there may be primes where you can't do it. There's another example, which is the example of the last lecture. I want to fix supersingular curve, C0 over K, at a prime. K is characteristic P. There's a formal stack, which I'll call M sub C0 hat, living over M. So this is the object that classifies deformations of C0. Right? Deformations of elliptic curves. So the way you interpret this is that this is something it makes sense to map not general schemes in, but you can map spec of R, where R is, say, a complete local ring, where, let's say, P is topologically nilpotent. So the sorts of rings I was using in the last lecture. So for those things, it makes sense to talk about the deformations. And the observation was that of the last lecture was that this has descent, not for all isogenies, but has descent for p power isogenies. And that was the stuff that encoded power operations. In that setting, I identified the associated category of modules over that gadget, things with descent. Let me use the sponge for those. And those were exactly, that was exactly describing the category of modules with power operations. Are there questions while I'm washing the board? Briefly describe a couple more, which are both relevant to topology. Let me describe this first one briefly. I hope to come back to it. We'll see. But it's an important example. There's a certain object called the Tate curve, which lives over spec of a Laurent polynomial, a Laurent power series ring. Let's call this Tate. Let me not say what it is, because it's hard to say precisely what it is. But this is this scheme is like a deleted formal neighborhood of a point. And this map encodes the deleted neighborhood of the cusp, this point at infinity that I could attach to the elliptic moduli stack to get its compactification. So in fact, you compactify the elliptic moduli stack by taking this guy and gluing in the undeleted disk, or some version of that construction. This object has descent for isogenies. There are canonical models of sort of all possible isogenies between Tate curves that you can write down. Let me not say how that is, but let me say that there's an associated cohomology theory, which is elliptic cohomology associated to the Tate curve, which is also called Tate K theory. The reason being is it's basically a souped-up version of K theory. So this is a version of elliptic cohomology which is secretly basically K theory. This has an equivariant version. So Noriganter produced by means of using the fact that's really described by K theory, wrote down a collection of power operations for the equivariant version of this theory for finite groups. And the theory of such power operations are exactly encoded by the fact that we have descent for isogenies, and there's an associated category of modules for that. So equivariant Tate K theory let's say for finite groups, let's put a slot here, G is finite, takes values in modules descent for the Tate curve. This structure that I've implicitly defined, or implicitly pointed to here, is exactly what shows up here. I don't know if I'm actually, the way these lectures are turning out, I'm not going to have a lot of time to talk about that, but which is unfortunate because I find this the most revealing example for many purposes. Hopefully in the last lecture I'll have some time to explain how that works. All right. Let me do one more example just to give us a more concrete picture. So in the first lecture I mentioned the analytic moduli space of elliptic curves. So this was, I think I called it X mod gamma. So X is the double half plane. And gamma is GL2Z. And gamma acts on M by fractional linear transformations. And that's the model for smooth analytic elliptic curves. This has a universal curve, which I might write as E over gamma. E is a fibration over X, where E tau, the fiber over tau, is just complex numbers modulo the lattice given by tau, Z, and Z. Tau and 1. Well, there's sort of an you can easily construct an analytic model for M isog. So I'll let M be the following monoid, GL2Q, intersect integer matrices. So if you like, those are matrices, integral matrices with non-zero determinant. This monoid acts on X. The action of gamma on X extends to an action of M. In fact, it's given by the same formula, fractional linear transformations. And you can lift that action to this universal curve. So A of tau is given by the usual transformation, where it's the matrix ABCD. And over, on the curves over it, we get a transformation from the fiber over tau to the fiber over A tau, and that's given by a formula. Just write it out. And this formula implements an isogeny of degree determinant of A. So this actually carries the universal example of an isogeny. So M and isog is actually isomorphic to, I'll take M times X, and I'll divide out by two different actions of gamma. One, if you like, corresponding to the source, and one corresponding to the target. And that's a model for the analytic version of this. And then you can actually build the whole that one could make that is sort of motivating this story. So back in the first talk, I pointed out that if you have an étale morphism to the elliptic moduli stack, the machinery of Gorse, Hopkins, Miller, Jacob-Lurie, whoever you want to put, says that out of this you can construct a commutative S algebra, whose pi 0 is A, and which is an elliptic spectrum associated to this particular elliptic curve. You might want to ask, well, what if, let's call this a conjecture, question mark. Let me make a conjecture that says what you're supposed to get if, I should have said, Lurie, of course, says not only do you get an elliptic spectrum, you get a derived elliptic curve, and you also get equivariant elliptic cohomology theories for every group. That's what comes out of this machine. But let's suppose, in addition, that this map has descent for isogenies. And it satisfies the Frobenius congruence. I haven't talked about the Frobenius congruence today, and I don't want to, but at all primes. I talked about it in the previous lecture, in lecture 2, and for that particular case. And it's the same statement, but for this case. Then what you might expect is there exist the equivariant elliptic cohomology associated to C for finite groups should be represented not merely by equivariant spectra, but by an ultracommutative global spectrum. So I'm not going to talk about ultracommutativity in global spectra very much because I don't know much about it. And there are people in the room who know much more than I do. But this is a kind of fancy multiplicative structure on a spectrum that represents equivariant cohomology theories for all groups, in this case all finite groups. That structure is supposed to give you power operations. And the conjecture is somehow you could go backwards. Not only should that structure give you power operations, which gives you this algebraic geometric shadow, but in some nice setting where you're étale, you should probably be able to go the other way. This conjecture has the feature of being not obviously wrong. I don't know anything that goes against it. And I know little bits that are true. For instance, the examples I referred to up there. All right. So I wanted to talk about this Koszul business. I have to say a little bit about what Koszul duality is. Or actually, I said quadratic before, but it's really.
Can I just ask
yes.
something? The Frobenius congruences,
Yep.
were they implicitly already in what you discussed before the break? Or is this something
No, that was. I did not mention it in what I said before the break. Frobenius congruence is an additional condition, which, if you state it in terms of rings, so assume I have a spec A over C and it has descent, so I have these rings A isog P. There's a particular map from A isog P to A mod P that classifies the pth power Frobenius. And the Frobenius congruence, let's see if I can even remember what this is. It says, I have the map T that represents the target of the isogeny. I have the projection from A to its quotient, and I have the absolute Frobenius, because A mod P is characteristic P. And this classifies the Frobenius isogeny. And the Frobenius congruence is that this commutes. That's effectively the condition I gave in the last lecture.
And how about the theta?
The who?
Are there the theta P, theta I?
So I don't have to say, I believe I do not have to ask for thetas, for witnesses for the congruence in the statement of this conjecture. You can, there's reason to think that you don't have to specify that because I said étale, then for free, I don't have to provide witnesses for the congruences, they will automatically exist. I don't know that's actually true in this context, but I know it's true for lambda rings. And so I expect the same thing to work here. So that's a little thing, but I think it will work out. But that's a good question, actually. Okay. I'm going to talk about this Koszul business. So I have to say a little bit about what Koszul duality is, which is hard, because everybody seems to think about this differently. Also, I was looking in literature, Koszul duality is actually used for several different concepts, which are not precisely identical to each other as far as I can tell. So one thing it's often used for, it's used as a synonym for what's called Bar-cobar duality, or what I would call that. Let me just give a very rough idea. This is meant to be rough. So let's say I have a coalgebra. So I'm going to start with a coalgebra, which is weird. We usually start with algebras because that makes us happier. But in my example, I have something that looks like a coalgebra. So I'll start with a coalgebra. And for making this easier, let's think of it as over a field, just to get the idea. And then if I have a comodule, I get to produce a cobar complex. This will be the cobar complex, where'd it go? C, let's see, of M, A, K. So this is some kind of chain complex, I guess a cochain complex, where in the nth degree, I'll take a tensor product of copies of A, and then tensor it on both sides by K. And then this is a let's call this N. degree n. I put A bar, so I'll use the co-augmentation co-ideal. So I'll get the reduced Kobar complex. Not that it really matters for this discussion. This, of course, is supposed to compute the derived cotensor product of a left comodule and a right comodule over A. Let me put an upper H to say it's derived. And so I don't have to figure out if it's supposed to be left derived or right derived. This one's right derived, but I'm not really sure. It doesn't matter. The observation, of course, is that if you carry out this construction, this is a chain complex, this object itself becomes a module over a differential graded ring. So let's take B to be the Kobar complex K, A, K. And this is a DGA. And this guy is a module over B. Actually, we could have actually plugged in a differential graded comodule, and I would still get this to be a differential graded module over B. Let's say it's a B module. In fact, if I want to be really fancy, I could even start with a differential graded coalgebra. I would still get a differential graded algebra. The observation is that this construction, therefore, gives you something that goes from some derived category of comodules over A to the derived category of modules over B. The fun thing is that by the process of turning arrows around, you could actually run this story in reverse. You could start with a differential graded B module and then take a bar construction on that. And that turns out to be a comodule over the bar construction on B, the small bar construction on B. And that's somehow would be, that would be naturally a comodule over something. The ideas of Bar-cobar duality is that this thing wants to be in equivalence. Let me just say it like that. Unfortunately, a precise statement requires adding adjectives or possibly replacing these with nice full subcategories. And everyone seems to do that differently. So I don't actually know sort of what the best thing to say is. But in practice, we observe that there's sort of a nice relationship between these two categories. So that's that. That's all I want to say about that. Think about this relationship. Now, this is what I would call Bar-cobar duality. Koszul duality is a situation where this works out very nicely, and sort of comes with methods for calculating things. That's another board. So let's consider the case where my coalgebra A has a grading. Yep. The one thing that could be its inverse is the bar construction on B. Yeah. I want to be careful because it's possible that if I do the bar construction on B, maybe I don't get C back, but I get something close to it. Care is needed to make an explicit statement. I don't want to make an explicit statement, so I don't want to be careful. Actually, the implication goes the other way there. But that's sort of the picture. I'm not really going to use that picture, but that's sort of what's behind it. Let's suppose A is graded. Okay? Let's say the bottom part is just K, so it's graded and co-augmented. Then the DGA B also admits a grading. Apparently, I'm going to actually put brackets on these gradings just so they're not confused with some different kind of indexing that might be around. So I'll use brackets for the grading here. Yeah, so let's assume it's positively graded. It's connected. And then B has the same thing. Let me draw a picture. So let me write down the Bar-cobar complex. So I'll do it in columns. So the bottom of the Kobar complex, this is B, remember, is K, A, K. So the bottom is just K. I just have A0. This is column 0. Column 1 is A bar. So that's a direct sum of A1, A2, A3, and so forth. Column 2 is A bar tensor A bar. So in grading 2, I have A1 tensor A1. In grading 3, I have A2 tensor A1, direct sum A1 tensor A2, and then there's more stuff. And in grading 3, well, sort of in degree 3, I have A1 8 bar tensor A bar tensor A bar. The bottom graded part is that, and then there's more stuff. So the horizontal things are this new grading that I've defined on B. So these are the B subbracket R's. And these are all cochain complexes. The nice feature is that the differentials in the cobar complex preserve the grading for this small cobar complex that I defined up there. The differentials are built as alternating sums of the maps that come from the coproduct on A. Okay. So we say that A is Koszul if the homology of the rth graded piece of this cobar complex is 0 if the dimension is not R. Or in other words, we say it's Koszul if all of the cohomology here is concentrated along the diagonal. This is at least my favorite definition of Koszul. Other people have other ones, but this one I like because it sort of immediately leads to every property of Koszul that you want. So let me give some properties. So for instance, what this does, it produces an object, I guess actually a quotient object of B that's quasi-isomorphic to it. So if I write C sub R to be the rth homology, so the one group that may be non-trivial, then the CRs form a ring. It's an algebra. And in fact, we get a quasi-isomorphism from the differential graded algebra B to the differential graded algebra C, where what's the differential? Well, if I take the there is no differential. This is the object with D equal to 0. That's basically a spectral sequence argument. So it immediately gives a formality result for B in a very particular way. So the classical example, which probably everybody knows, is the example, I guess, due to Koszul of the symmetric algebra. So let's A be, well, the symmetric algebra, except for some reason I'm doing coalgebra, so it's the dual of symmetric algebra, which is a coalgebra. And then I take the cobar complex. But then I discover, gosh, it's Koszul. And in fact, if I carry through the calculation, I discover that the thing that I get is exactly the exterior algebra on V, or V star, I guess, with trivial differential. So of course, this immediately gives the calculation for various homological things about the symmetric algebra. Sort of this. I guess the V gets shifted by a degree. I'll put -1 here, although possibly it should be 1. All right. One payoff of this is you immediately get a Koszul complex. So given an M, which is a comodule for A, I get M, which is quasi-isomorphic to the cobar complex on A. But that, in turn, is quasi-isomorphic to a smaller complex that's built from these C's, which you can write down explicitly. Basically, the idea is that if I take this idea and I apply it to this object, I don't get a graded object, but I get a filtered object. Filtered objects have special sequences. In this case, the E2 term of the spectral sequence, or actually the E1 term, is concentrated on a diagonal. So it's just a chain complex. It's that chain complex. Koszul complex. All right. Another consequence of being Koszul is that it automatically implies that your original coalgebra is quadratic in the sense that I described last time. it's generated or co-generated by degree 1, that's the fact that all these maps are injections. That's what that means. So there's no homology in these spots and further down, so it's co-generated by A1. And given that it's co-generated by A1, it turns out to have only relations here. The relations are entirely encoded by this inclusion. Co-relations, I should say, because it's a co-algebra. There's no homology in the second column lower down, and that's the fact that there are no other co-relations. If you don't like that, turn the arrows around and think about algebras. It's a little bit easier to process what I just said. But it's the same story. And then sort of Koszul tells you that some other homology is also there, so it gives you sort of some sort of more strong version of being quadratic that is sort of good for homological algebra. All right. I guess there's more I can say, but let's leave it at that. So I've basically told you how, given a suitable, there it is, given a an object with descent for isogenies. I'm going to just restrict to the case of p isogenies now, peak power isogenies. That's the one relevant for the previous talk. Anyway, it's also the easiest to think about. So in some sense, I've produced for any object that has descent for p isogenies, I've produced a category of, I called them in the last talk, I think, isogeny modules with descent. So given spec y, or spec a, let's say, over M, which has descent for p power isogenies. So remember that implicitly means I have a bunch of rings called A isog p to the r. Now I'm just going to call them A sub r. And it's basically a coalgebra. There's actually a subtlety. It's a coalgebra, if you like, over A0, which is really A. So it's a coalgebra. It's actually a coalgebroid over this thing. It's co-augmented and graded, but it's a coalgebroid because there's a left and right unit. That actually changes nothing about the formalism I just told you. It works just as well. And so we therefore can produce an object I'll call B. B direct sum brackets R. And let's actually write the collection of BRs. And this is this Bar-cobar complex. And this is what I'm going to call the modular isogeny complex.
This also has an oid direction now?
Has a who?
Is this an oid thing with source and target different?
What was that word you said?
I don't know what it is. You have to invent something. So first it was the coalgebra.
Yeah, so this thing is different. This thing has, remember, it's two different maps, a source and a target, instead of a single map.
A plane ring, or does it also have sort of...
Who is a plane? The B is also it turns out to be a ring, but it contains A0 in some sense, but it's not central. Unfortunately, the picture you get in the dual is not precisely analogous to the thing you get downstairs, but it's a ring. It contains A0, but A0 is not in the center. That's how you see it. I think that's right. I think that's right. I'll, to be honest, I don't use, I've never really worked much with the algebraic structure on this because it's never been convenient to do so. Although in principle you can. I think that's right. So this is this object. Anyway, there's a theorem. Theorem, which is that for any such A, it's Koszul. i.e., the analogous fact holds. The homology of these B brackets R's is 0 if star is not equal to R. Furthermore, let's write CR for the Rth homology of B brackets R. And then we have, in fact, CR is 0 if R is greater than or equal to 3. So most of the CRs are actually 0. And also, these things are finite, free, locally free, flat, I don't know. They're locally free, let's say left A0 modules of rank 1, p plus 1, and p, respectively. I say left to be specific because the CIs turn out to be bimodules for A0. They're also free as right modules with the same rank, but let's just be specific. So you don't have to worry about which is left and which is right. It's the same story either way. Okay. This implicitly implies the claims I made in the previous lecture about power operations from Rav E theory, namely that it was quadratic, because in fact it's Koszul. And Koszul implies quadratic. All right. So A, let's call it A star. It's the collection of all these things viewed as some kind of coalgebroid.
So this notion, you just define it for coalgebras, but
we can make it work for coalgebroids. I did that just so that you wouldn't get sort of too tense when I was talking about it before. But in fact, it does work. It's really sort of a lot of the formal construction just uses the fact that you have a tensor product. It just needs to be associative. There's no commutativity. And so the property of being Koszul is a property that you observe. It's either true or false. So there's just not much to say in general about how you generalize it. It's this. It's what's up here. So if you look at the columns are K, A bar tensor A bar, A bar tensor A bar tensor A bar. So one thing that is a little bit subtle, but it's not really hard, is you have to now make sense of that even if in this coalgebroid setting. But it looks exactly the same. So what I've done is if I look at a tensor product of A bars, each A bar is graded. And therefore, that implicitly supplies a grading to the iterated tensor product of A bars. And that's what I've separated out the iterated tensor products of A bars in each column according to their grading. And then that's the grading on the B. The observation is that the boundary map in the Kobar complex respects that grading. That's the only observation. It's just an observation about the boundary. It's important that it's the small bar complex KAK that is the structure I'm using at the ends I'm using a certain augmentation. So for the A star in question, I have to use a certain augmentation. There is a question, which map from A star back to A0 am I using in this case? And I didn't tell you what that was. But it's the map that sends A0 to itself and sends all the ANs for n bigger than 1 to 0. It's the thing that, well, anyway. So actually, it's a co-augmentation. So that was probably actually bad. I probably had the arrows reversed in what I just said. So there's a precise statement that one can make that is precisely the generalization of what I did if I'm over a field, over a commutative ring, and I don't have this left and right unit. All right.
Sorry, this M over here is for elliptic curves or for formal groups?
This is elliptic curves. So I'm stating the one for elliptic curves. That's what the theorem's about. But there's also a statement for formal groups, which I'll give later. Okay? All right. What? What's wrong? All right. I want to give an idea of why this is true. All right. What? Hmm? Yeah, it has something. It exactly has something to do with the height. It's exactly because the largest. It's related to the fact that the largest height you'll see in formal groups is height 2. Really, it's the fact that the underlying p-divisible groups of elliptic curves all have height 2. That's what that is. Yep.
So this P of C2 is equal to P plus 1 squared minus P squared minus P minus 1?
P of C2? What's P of C?
This is 1 P plus 1 comma P.
Yes?
Is it P plus 1 squared minus the number of points?
Probably. those numbers come from playing around with generating series. So if you write down the series polynomial on t, actually, 1 plus t times 1 plus pt, I get a generating series that spits out those numbers. If I take the reciprocal of that and change the sign on t, I get a generating series that gives me the ranks of the ARs as modules over A0. And that's not an accident. The fact that it's Koszul, the fact that I have this vanishing cohomology, implies that relation between Poincare series. So that's actually how you read off those ranks. So I don't have to tell you that part of the proof now. I just told you it. So just counting. All right, how am I doing? Oh, dear. OK. So let me write down. So before I was using all isogenies. Now I just want to use p power isogeny. Let's call it m isog p star.
Is this a proof or is it something?
It's a sketch of a proof. I want to give an idea of why it's true. Proof. Ish. All right. So this has an associated simplicial object, just like the one I built for all isogenies, but I'll just use p power isogenies. And now let's suppose that y, which is spec A, is equipped with descent for p power isogenies, and then there's an associated simplicial object y dot that lives over m dot. That was the formalism I set up in the first half. That was encoded by some map of simplicial objects. So the first observation I have to make. So understanding having this gadget implicitly gives me all these rings AR in the coalgebra structure. It's more or less a direct translation of what that is. Let's see, do I have it? I erased my complex. I was going to leave it up right until this point. So I would have that to point to. In that Bar-cobar complex, I had differentials. I did not write down the differential. I said there were alternating differences of various co-multiplications. The important observation is that I don't need the full simplicial object in order to write down that complex. I just need part of it. So here I'll write down the part of y I need. So I have this sequence of objects, y0, y1, and y2. And I have two boundary maps from y1 to y0, source and target. But I'll just write down one of them. I have three maps here. I'll just write down two. I have four maps here, but I'll just write down three. So the construction of B only uses this part of the simplicial object. In each case, I have, some sequence of isogenies, C0 up to C whatever, in this case C3, and I have face maps. A face map will sort of leave out something or compose something. I want to make sure that I always keep C0. So the three different face maps here I can put C2 in because there's only three of them, are C0, C1 to C2, C0 to C1 to C3, or C0 to C2 to C3. I don't use the face map that forgets about C0. I keep C0. I always keep the source in my sequence of arrows. I always keep the first object. Okay, that's all I need to construct B. That's important. It means the following. It means I can construct this complex B not merely for things that have descent, because I don't need all that structure. In fact, let me see how I want to say this. So given any A0 to R, a ring homomorphism, I can construct B brackets R tensor. Let's actually do it like this on the left, because I think that's how I want to say it. In other words, i.e., this fancy statement was basically a way of getting to the fact that the B brackets R's are actually complexes of A0 modules. Despite the fact that I'm using all these ring homomorphisms and they're different ring homomorphisms. I'm only using the ones that are actually maps of A0 modules. I have some ring homomorphisms in this story, like the T, the ones that classify target, that aren't A0 module structures, where the A0 module structure comes from the source. So let's put S here. B brackets R is a complex. Probably. B is, roughly speaking, approximately spec B is this. That's maybe the relation. It's a simplicial object. Approximately, because I actually did something. I got rid of degeneracies in my cosimplicial ring, and in fact, I flattened it to a chain complex. But if you forget about that, it's basically spec B. Spec of that cosimplicial ring is Y dot. That simplicial stack. Okay. All right. So the observation is, first of all, I can actually do this. So what I'll do is the following. I need to compute something with the homology of B sub brackets R. I also know that the modules in B sub brackets R are all finitely generated free modules over A0. Sorry, locally free modules over A0. So I can use sort of basic commutative algebra to reduce to the case, basically Nakayama's lemma. I can reduce to showing that the homology of K tensor over A0, B brackets R, is concentrated at 0 if star is not equal to R for A0 mapping to K, where K is a field, maybe even an algebraically closed field. It's just sort of basic commutative algebra, because it's a complex of finite locally free modules. It's bounded. Use Nakayama's limit to make this reduction. So this is what I'll do. I'll explain why this is true. So there's an interpretation of what these complexes look like. I'm fixing a single elliptic curve over some field K. So if you like, I've given myself spec K that maps to Y0, and then that maps to M, and I'm going to fix that elliptic curve. In fact, in what I'm going to say, I don't have to worry about Y anymore. This is just a property of the fixed elliptic curve. This is just something about the fixed elliptic curve over C. Let's see, blah, blah, blah. What I want to say? Oh, let's just say what this looks like. Let's suppose there are two cases. So remember, I'm using, I started with something that had descent for P isogenies. So I'm interested in P isogenies. So there are two cases. Case 1 is that, and case 2 is this. Characteristic P and everything else. Case 1 is completely formal. It's basically combinatorial. So in case 1, if I have an elliptic curve over an algebraic closed field, I understand its P torsion, or its P power torsion. I understand all subgroups of order of power of P, because the P power torsion in this elliptic curve, in fact, let's just write P to the infinity, the union of all the P power torsion, that's QP mod ZP squared. And to recognize subgroup schemes, I just have to give you actual physical subgroups of that group. So for instance, for this thing, so for the AR, and I should decorate AR by the curve C. It's the AR for this curve C. So this is an algebra over K. This is actually a product of copies of K indexed by all the subgroups of physical subgroups of this discrete group of the appropriate order, in this case P to the R. That's all it is. Similarly, the associated complex you get corresponding to the B's, which is built from tensor products of these, that complex involves rings which are products of K indexed by flags of subgroups. Let me not do the argument to show the theorem in that case. It's a classical argument. The one key feature of the argument that you discover is that you discover that you can divide this complex into pieces. If you have a flag of subgroups, you can sort of just fix the largest group and consider a bunch of a complex which all share the largest group and the biggest group in the flag. If that largest group is not elementary p abelian, the associated subcomplex is acyclic. The only subcomplexes that contribute something non-trivial are the ones that are elementary p abelian. That's why you only see something in ranks 0, 1, and 2, because those are the only ranks of elementary p abelian subgroups in here. Only zp to the z mod p to the k's inside here. So, and that's just a purely combinatorial argument. The generalization of this argument to arbitrary, instead of 2, you have n up here, is basically a calculation of the cohomology of the Tietz building for GLN, Z. No, GLN, Z mod P, excuse me, which is a well-known calculation. So that's purely formal. However, this leaves the case where we're in the characteristic, and that's actually the most interesting case for me. That includes the supersingular curve case. So let me just do the supersingular curve case, which is the most important one. This is yes, yes. It is. The observation is that it is extra structure, but for the calculation of the homology I need, I don't need the extra structure. I can actually, the whole B brackets R does not use that extra structure. To do the particular homological calculation I need to do, I don't need the extra structure. That's the observation. Although Y itself has extra structure that encodes how to push forward things along isogenies or whatever I said. For this particular calculation, I get to throw that away. In other words, this is a calculation that you can do on the moduli stack. You can pull it back over any curve you like and do the calculation there.
But wasn't
B was this B was a chain complex. So B one thing. So I alluded. I said that. So it's a little bit tricky. I said that B would. I implied, I think, in my Bar-cobar duality argument that B would be some kind of algebra, but actually that's not always going to happen. B is only going to have an algebra structure, only have a multiplication if I'm in a context where I actually have a descent. If I don't have that, it won't be an algebra, but I will still at least have the chain complex. I should have said here, I mean, I sort of rushed a little bit. I better say something. You know, I wrote down these iterated tensor products, right? These are the things that are inside a B brackets R in some degree, right? This ring classifies something. This classifies, say I fix an elliptic curve, it classifies chains of subgroups. That's one way to say what these things are. And the subgroups have prescribed ranks. Those are the subscripts R. Actually, it's the quotients in this case. I think. Yes? There's a bunch of structure maps. If you use the language of subgroups, there's two things you can do. You can take a subgroup and G1, take the quotient of C by G1, and also take the quotient of all these other subgroups. So I can take G2 mod G1, and then G3 mod G1, etc., all the way up to C mod G1. But there's a bunch of other things I can do which involve omitting one of these subgroups other than G1. So I could take G2, G3, up to C. Or I could omit, sorry, I keep G1. I want to keep G1, but I'll omit G2, go up to G3. Or I could omit whatever comes after G2, etc. So there's a bunch of simplicial operators that omit something but keeps G1. On the other hand, there's the thing that quotients out by G1. To form the B, I only use these operators. That's the difference. The extra structure is here. This is the one that has this extra structure you're worried about, but I'm not using it to form the B complex. So I get to do a calculation where I don't need to keep This is actually a thing that encodes the thing where I push something forward by an isogeny. The rest of it just encodes the way that you can compose isogenies, but doesn't really remember how you push things forward. That's really the way you think about it. And this Koszul property that I'm trying to prove only uses this other stuff. If I didn't have that, there would really be, I wouldn't know how to prove it. Okay. Sorry, that was, where am I? Oh, case 2. So I'm in case 2 here, which is going to be a supersingular curve. Let's just worry about that one. There's also the ordinary curves, which are the ones whose formal group is height 1. And I know this as a calculation. So it turns out for case 2, instead of picking a supersingular curve, I'll actually pick a deformation of a supersingular curve. So I'm going to use, so I'll have a supersingular curve. But what I'll take is I'll take A to be K adjoin a power series ring. And I'll take the map from spec A to the moduli stack of elliptic curves that carries the universal deformation of C0 to a ring of characteristic P. That lives over this. In the context of the previous talk, this was the ring from Ravi E theory. And I'm just taking it mod P. So this will be the universal deformation of C0 to a ring of characteristic P. And now I need to understand this complex. And to do this, I need to understand these associated rings A sub r. Again, A sub r should always be decorated by whatever elliptic curve is in the background. I'm sorry, I didn't include that in the notation. I probably should have set that up. So I'm using this particular curve, C univ. And associated to this are these rings AR. In this case, this is a calculation. So let me write down A1. This is K adjoin 2 power series variables. And I mod out by a polynomial A to the P minus A prime times A minus A prime to the P. And more generally, AR is similar. It's a power series on 2 variables, A and A prime, mod a more complicated polynomial. Let's write it this way. It's the product of A p to the I minus A prime p to the j. And that product is over I plus j equal to r. So that's just a single polynomial. This is proved in the book by Katz-Maser on arithmetic moduli of elliptic curves. It sort of encodes a feature. They, of course, think of it in terms of the geometry of the modular curve for p power isogenies. This first one, I think I'm supposed to point out, is famous to people who knows these sorts of things. It's kind of an avatar of something called the Kronecker congruence. He observed that if you look at the modular curve for p isogenies in characteristic p, I don't know how he actually said it, but this is how people say it now, then associated to elliptic curves, there's a modular function called the J invariant. It's really a modular form. And if 2 curves are related by a p power isogeny, and I write J and J prime for their J invariants, which are elements over the field they live in, then, or over the ring they live in, then the same identity holds. This is congruent to 0 mod p. And this is a generalization of that fact. So it's really a version of some classical fact that's describing the nature of the modular curve. The picture that one draws is if you look at the modular curve in characteristic p, you have some special points which correspond to supersingular elliptic curves. And locally, you have a crossing. That's what this is describing. And at other points, which are ordinary points, you just have some curve, smooth locus. There. So I didn't actually say that this thing had descent for p isogenies. I'm just saying that these are the things that classify subgroups. In fact, it does have descent for isogenies. So there are source and target maps. Both of these rings are K adjoin A. This one is basically the obvious inclusion. A goes to A. And the other one sends, this is source, and target sends A to A prime. And actually, I also have to be careful about scalars. This one is identity on scalars, let's say. This one is p to the rth power on scalars. Scalars are k. So this actually, this is actually describing power operations from Morava E theory as long as I reduce mod p. It's describing the full theory. You can do this at every prime using this observation. So I told you last time an integral calculation of the prime 2, and those are only known at a few primes to my knowledge, but this you can do at every prime. So I proved the theorem for supersingular curves by actually constructing the full theory of power, giving a complete description of the theory of power operations from Morava E theory mod p using Katz-Maser.
Where the space is trivial.
The space, what's the space?
Power operations.
I mean, when I say describe the theory, I want to, I'm not calculating the power operations on a space. I'm saying what are the rings involved in the power operations. That's what I mean by the theory. I'm not calculating this on a space. Right. How am I doing? Oh, my goodness. I have 3 minutes. That's time to do something else. Right? I did allude to one thing. Huh? I mean, I could ditch. So I had a topic for Wednesday's talk, but I could ditch that and continue on this line, or I could just do something different on Wednesday. But maybe, let me say one more thing, because, of course, in lecture 2, I said that the power operations from Morava E theory were Koszul, or sorry, I said they were quadratic, and they're also, in fact, Koszul. But that works for every height. And I've only proved this at height 2 with this proof using Katz-Maser. So let me just briefly indicate what you do for arbitrary heights, because it's completely different. So the proof I just gave, or indicated, for supersingular curves use geometry. But the general proof is a topological proof. And I don't know how to write it in terms of algebraic geometry. Let me say it and give the idea in as few words as possible. And then we can go have some coffee. Let's see. Oh, I'm not going to get to talk about that. That's so sad. Yes? I did. I showed you the argument for a supersingular. I didn't finish the argument. I'm sorry. The punchline is that now you have this explicit stuff, and now you calculate the complex. So you go and write down and explicitly compute the cohomology of the complex B constructed from these rings, and you get the right answer. So at this point, after this point, it's a calculation which you don't want to see. Okay. Sorry, I did. You're right. I left out the punchline, but the punchline is a letdown. It just says, okay, now you have this. Now you calculate something. You calculate an explicit chain complex. We all know how fun that is. What? It's not fun? Come on. All right. So for a general Morava E theory, associated to a formal group of height h, finite height. So there were analogs of this construction. So we had these rings AR, which were topologically the quotient of the cohomology of the symmetric group by an ideal generated by transfers, and which we had an interpretation as classifying subgroups. Or if you prefer, classifying isogenies that deform a power Frobenius. So this classifies subgroups of rank p to the r of a deformation of G0. Deformation to some ring. Okay. So I want to show the analog of this. So I have to construct this complex. And there's a sort of a construction that goes through topology. So here's a construction. So let's take X is going to be a finite set with a sigma m action. Let's observe that if we take a finite set with a sigma m action, we can take the Borel construction in that finite set and then take the E cohomology of that. So that's the Borel cohomology of X. Morava E theory Borel cohomology. That's a thing I can do. Here's another thing I can do. I can consider a very particular finite set, which I'm going to call sigma m set, which I'll call 2 to the m minus 2. Sigma m acts on it. Guess how many elements this set has. What is this? This is a subset of a certain set with 2 to the m elements. This is the power set. I'm going to remove 2 elements from the power set, the ones you think I'm going to remove, the empty set and the whole thing, the top and bottom elements in the poset. Okay, the symmetric group acts on this. Actually, if you think about what this looks like, this divides up into orbits corresponding to non-trivial partitions of the set into two pieces. And the stabilizer groups are sigma I times sigma m minus I. That captures those subgroups that showed up before. And now we'll make a definition. Q m of some finite set X is defined to be, it's going to be the quotient of this Borel cohomology of X by the Borel cohomology of X times 2 to the m minus 2, where the map is the transfer. So if I take the product with this finite set, I get a covering map, a finite covering of degree 2 to the m minus 2. And there's an associated transfer in cohomology. So I'll take the quotient of that transfer. So this Q is some construction. It's not a cohomology theory. I only defined it for finite sets. I could have defined it for any X. It's not really a cohomology theory. But it is an example of a Mackey functor. That is, it's a functor of finite sets. But it's also compatible with transfers. So it also comes with transfers for any map between finite sets. It's a Mackey functor for sigma m. And so the proof of the Morava E theory version of this follows from, so let's do an obvious check here to see if this is relevant. What's Qm of a point? Well, this will just be the cohomology of B sigma m. This is actually the direct sum of a cohomology of B sigma I times sigma m minus I. And the image is precisely the quotient of this by the transfer ideal. So when m is the power of p, this is the ring I called AR. And so the two observations, and I'll just make these observations and then stop. So associated to this A is a modular isogeny complex of the same type I defined for elliptic curves. It's the same formalism. I can compose isogenies of these things. So let's call that B brackets R. This thing is exactly Q applied to a certain simplicial set. The simplicial set is a version of the partition complex. I'll call this P bar sub P to the R. Is that what I want to call it? This is what I'll call the reduced partition complex. So I'm going to take the nerve of all of the category, the poset of partitions of a finite set of order P to the R. I'm going to divide out by some subcomplexes any simplex that contains the bottom element or which contains the top element. I'll collapse to a point. Elements in the poset. A simplex is a chain of elements in the poset. So if it contains one of those, I'll kill them. That's the reduced partition complex. The first observation is that the modular isogeny complex actually comes from applying this Q to the simplicial set. The associated cochain complex is BR, isomorphic. The second observation is, well, now I have to compute, the homology of this. So this, of course, is the cohomology of BR, which is the cohomology of this complex. This has another name. It's the Breeden cohomology of the reduced partition complex with coefficients in the Mackey functor Q. And the second part is to observe that this thing vanishes in the appropriate dimension. And the best proof of that follows from results of Aron, Dwyer, and Lesch. This vanishes, except when star is equal to R. This just uses only some properties of the coefficients Q. So this is a general fact. It's a particular instance of a general theorem they prove. Q, in particular, it definitely needs to use the fact that Q is a Mackey functor. So I'll emphasize that, and there's some other properties. But I'll emphasize that because that's sort of the thing that wasn't in my algebra geometric picture. I talked about these objects, BR, and these rings, AR, and all this stuff. But I didn't have anything that in topology corresponds to the transfers. But they're there, and if you use the transfers, this theorem falls right out. So that's the extra thing that works in topology that means you can prove this in general. I had a proof of this. My original proof of this, I'm very fond of it, but it's much more complicated. And this is a much better way to see it. Just apply their theorem. This second part. So that's how you prove it for that. Okay, I'll stop here.